right, let's get started. Good afternoon. Welcome to today's seminar for science writers on the 25th anniversary of the Hubble Space Telescope. I'm Rick Fienberg, AAS press officer, and we're here in Seattle, Washington on the third day of our very busy meeting. This is not exactly a press conference. It's a seminar for science writers, which means that it's not, well, first of all, you're not going to get blockbuster news from Hubble. You already got that over the last couple of days. And those images are now appearing on front pages of newspapers all over the place, and that's very gratifying. This is a backgrounder. It's a backgrounder because this coming year, well, this year now, 2015, is the year of the 25th anniversary of the launch of the Hubble Space Telescope. And my friends at the Space Telescope Science Institute and NASA Goddard, in particular, Ray Villard and Cheryl Gundy at STSCI, orchestrated putting this seminar together, and I appreciate that. Thank them for doing it. Everybody who covers astronomy covers Hubble regularly, but if you've been covering it for a long time, like I have, you probably forgot some of the stuff that happened early on. You may be thinking now about, exoplanet atmospheres and things, and forget some of the phenomenal discoveries that were made early on. So we're going to get some reminders of that. We're going to hear about different aspects of Hubble that you might want to cover if you do a retrospective in the coming year, and a little bit about where we go from here in the future. So we have, as always, we'll be webcasting. So if you're on the webcast and you want to ask questions, please remember to use the text chat. We have 5 speakers today who are representing NASA institutions and the Space Telescope Science Institute. We're going to start out with Jennifer Wiseman from NASA Goddard, who will be talking about Hubble's classic achievements. Then we'll go on to Kenneth Sembach from STSCI, talking about Hubble's unexpected accomplishments. Melissa McGrath from NASA Marshall will talk about exploring the solar system with Hubble. Jennifer Lotz from Space Telescope Science Institute will talk about Hubble's deep surveys. And then Jason Kalirai, also from STSCI, will talk about how to make Hubble even more powerful in the coming decades as other new, larger space telescopes come online. So with that, I will turn it over to Jennifer, and we'll get started.
Okay, thank you. This is a really great year for Hubble. Almost every year is a great year for Hubble, we think. But this being the 25th anniversary, we're particularly excited to talk about not only what's been accomplished with Hubble, but what we are accomplishing with Hubble and what we will be accomplishing with Hubble. Because Hubble right now is as scientifically powerful as ever, perhaps more scientifically powerful than ever. So we're celebrating that this year. All right, my part in this presentation today is to talk about the early years of Hubble and what had been expected from Hubble and hoped for, and what came of some of those ideas. And then we'll move on with Dr. Sembach here talking about the many unexpected discoveries that we've also made with Hubble. So as we look back to the early years and before, we ask ourselves, why a space telescope? And there have been many explorations into that question, so I won't try to play historian here. Robert Smith wrote a great book about the space telescope, which I recommend. But just a couple of tidbits here. Even back in the 1960s, there was a National Academy study led by Lyman Spitzer, and the result of that was what was informally called Chairman Spitzer's Little Black Book, reporting the results of that study on scientific uses of a large space telescope. And that then blossomed into a NASA decision to go forward with a space telescope. And the first announcement of opportunity was put forth in 1977, listing ideas for science instrument teams and instrument proposals, and also for participation in the mission in other ways by scientists. And that proposal, or that announcement, included more than 20 examples of the kinds of science you might be able to do uniquely from space if you had this kind of capability. And some of those issues, as they developed to the point of launch, we've gone here from 1977 to 1990 when the mission actually launched. Those issues matured and developed. Some of those key issues that were on the minds of astronomers at the point of launch back in 1990 or were listed here as examples. Things like the distance scale of the universe and what is the rate of expansion and therefore the implied age of the universe. What are the properties and distribution of gas around galaxies and between galaxies? What about supermassive black holes? Do they exist? Do they exist in the core of galaxies? And what would their relationship be to active galactic nuclei and quasars? What about the properties of stellar populations, both in our galaxy and other galaxies? And what about the structure and properties of regions where stars form, star-forming regions, both in our galaxy and others? And then, of course, interest in our own solar system. What are the properties and how do they change with time of planets, comets, and asteroids right in our own solar system neighborhood? So I will bring to your attention a few examples of some of these topics from the early years of Hubble. And of course, if we're going to talk about star-forming regions, I can't help but point out the Eagle Nebula. This image released in 1995. Again, there was a burst of science released from Hubble right after 1993, the first servicing mission to address the spherical aberration problem on Hubble. That mission was completed in 1993. So in subsequent years, there was a burst of new science, new images coming forth from Hubble. And one of these iconic images that you're all aware of is this picture of the Eagle Nebula. On the left here you see the columns of gas that signify a region where stars have recently formed and are still forming inside those columns of gas. The image got the informal name of the Pillars of Creation, a grandiose title. And of course, I'm showing the new image on the right that we just released this week. So about 15 years later, or no, 20 years later, we have this marvelous newer image with a newer camera on Hubble. And you should also check out the infrared version of this image that was also released this week where you can actually see into the pillars. This gave us a visual clue as to the interaction of young stars that have recently formed, which in this image are outside these pillars, and how they're interacting with the dense gas remaining behind and maybe even impacting the population of stars still trying to form in these denser regions. Really gave us, for the first time, I think, a high angular resolution view of what's going on in star-forming regions. What about black holes? Well, early on, as soon as Hubble was fixed in the early 90s, the telescope was pointed toward the core of a very interesting galaxy, M87. M87 was known to be interesting because it had an active core. Let's see if I can get the little arrow here to work. And a very powerful jet emanating from that core. So what was going on? Could there possibly be something exotic, even a black hole in the core of this galaxy? Hubble was honed in on the core of that galaxy, of the gas there, and what was done was to monitor the motion of the gas right around the core. And so here in this image, you see the spectroscopic information of what's going on with the gas here. The astronomers used a spectrograph on Hubble to look at the gas on one side of the core of the galaxy and then also look at the gas. In this case, it's a line of nitrogen emission on the other side of the core. And they could tell that this gas was extremely shifted in its frequency. Red shifted on one side, which indicates motion away from the observer. Blue shifted on the other side, which indicates motion toward the observer. And we're talking really fast motion. So it's about 1 million miles per hour going off in one direction and 1 million miles per hour in the opposite sense on the other side. So this gas is orbiting very, very fast around the core of this galaxy. And from that, it was deduced that the only way something could be orbiting this fast, or would need to orbit this fast, in order not to fall in, would imply something very massive in the core within a very small volume. And so we're talking about at least a 3 billion solar mass black hole in the core of this galaxy that's driving the motion of this gas. So this was the first definitive observation of a black hole, a supermassive black hole in the core of another galaxy. Of course, we're now convinced that there's a supermassive black hole of some kind in the core of our own galaxy. All right, the repaired Hubble also had exquisite angular resolution that would allow us to look for individual stars, to separate them in crowded regions. And so in this way, you could actually study populations of stars and map out their properties. This cluster was observed in our little sister galaxy, the Large Magellanic Cloud. And by doing this kind of study, you can even see from the beauty of this image here that you can see star from star. You can discern star from star. That's what angular resolution and getting above the atmosphere will do for you. The astronomers who looked at this discerned from their studies of this star cluster that there were actually multiple populations of stars within this particular region. So one cluster of stars had formed, the massive stars had gone off in supernovae explosions, and that the pressure and the disruption from those explosions had incited another wave of star formation. They could tease all that out just from having high resolution images from Hubble. A major key program for Hubble was to try to measure the distance scale of the universe. And in fact, Hubble had some initial projects that were called key projects that were kickoffs for major science from Hubble. And one such team was led by Wendy Friedman, and her goal was actually to measure distances to galaxies. And we could use that distance ladder to then discern something about the scale of the entire universe and perhaps even the age of the universe. So this image shows you some of the data from that project. What the team did was to look for a particular type of star, a Cepheid variable star. And Cepheid variables are known famously for having a good relationship between their frequency of their pulsation and their intrinsic brightness. So you can use them as what we call a standard candle. You can tell how bright it appears, and then you know how bright it intrinsically is from its rate of pulsation, and that gives you a handle on how distant the galaxy is in which that Cepheid variable sits. So this is an example of M100, one of the galaxies that was studied in this project. And blown up here is an example of one Cepheid variable star in here. Now, of course, the key here is with Hubble, you can pull out an individual star and study it this way. And I don't know if you can tell from this image with the insets, but the brightness here is varying. And so the pulsing often happens in a matter of something like weeks. The team studied many, many Cepheid variables in many, many galaxies. This galaxy is at about 56 million light years away, but they went as far as over 100 million light years away with this galaxy, NGC 4603. And no, that's not a Cepheid variable. That's a foreground star in our own galaxy. But trust me, there are other Cepheids in there. This is very hard, right? Because by the time you get to very distant galaxies, you are pushing the limits of trying to discern star from star. But where this was all going was by being able to gauge the distance of these galaxies, using the Cepheid variable stars as standard candles, and then measuring their velocity by looking at the Doppler shifts of light from that galaxy, which can often be done from the ground. You can make a chart here, a Hubble diagram. And the Hubble diagram, which plots those parameters for each galaxy or set of galaxies, one against the other, you can come up with some sort of relationship, and this is showing you an early plot of that relationship for the Cepheid variables in this key project. The rate of expansion can be discerned from this plot, the rate of expansion for the entire universe, if you can correlate the distance of galaxies with their apparent recessional velocity, you can tell something about the expansion rate. And the key project team deduced an expansion rate of the universe at that time, or H0, Hubble constant, of 72, plus or minus 8 kilometers per second per megaparsec. This was a very important culmination. There had been passionate arguments from different teams of extremely highly respected astronomers who argued for different numbers and why they must be the case that varied by a factor of 2 or more. And so this result was profound, and it did, as the title of this talk says, it changed the textbooks. All right. So if you know the expansion rate of the universe, can you then kind of wind the clock back and just deduce how long it's been expanding? That is, what is the expansion age of the universe? And so we can do that little exercise. The key project team, as I just said, deduced from all their work for many years that H0 was 72. And then taking that number and combining it with traditional cosmological models, they derived that the age of the universe must be something between 9 and 12 billion years. Oops, this caused a big problem, you see, because in stellar astrophysics, the idea had come forth that stars needed to be, some of the oldest stars in globular clusters must be about 15 billion years old. So therefore you have this problem that the stars were older than the universe, right? You can't have that. This is a big problem. During all of this, astrophysics was advancing. I'm talking about sort of during the first decade of Hubble's life here, Hubble's missional life. Acceleration of the universe was discovered, which I'm just alluding to here, but this will be discussed more by Dr. Sembach. And therefore, this key project team could fold in those new observations into what kind of cosmological model they were going to apply as they considered the expansion of the universe. They then used a different cosmological model. We now call it the lambda cold dark matter universe. And using that new model, and also at the same time, the stellar astrophysicists had revised their understanding of the ages of the oldest stars, and we started to get a cohesive picture that the age of the universe is about 13 billion years, and that is what the key project team, led by Wendy Friedman, decided in their final paper in 2001. And that is, by the way, consistent with not only the revised ages of the oldest stars predicted by stellar astrophysics, but also the results of the WMAP mission and the Planck mission findings. All right, before we move on to the other speakers, I just want to mention why Hubble has had a litany of profound astrophysical successes. If even what I just said would have been more than enough for most people to appreciate a space mission, but we've had many, many years since those early findings, and the reason Hubble could work at all is because we were able to service it the first time, but we've been able to service it many times. And so this chart shows you the series of servicing missions, all involving the space shuttle, all involving the important interactions with humans, the human spaceflight program. The launch in 1990, this first servicing mission in 93, several more servicing missions, each time providing new capabilities or repairing capabilities on the observatory. The final one 5 years ago, I guess we're going on 6 now, which really put the telescope in fabulous condition. So we have a suite of instruments on Hubble now that's probably better and more powerful than ever before, and we're accomplishing science as never before. So it is this series of servicing that has kept Hubble at the forefront of astrophysics for all of these years. And Hubble has not only impacted science for all these 25 years, but it's also impacted culture around the world, right? So we see Hubble in everything from music and books and postage stamps and TV and all kinds of popular culture, to even just in casual conversation, everybody knows what Hubble is. So that's a good thing. I hope not just for the sake of Hubble, but for the sake of astrophysics, astronomy, and the world's understanding of science and the beauty of the universe that we live in. I think that speaks well for the mission and all the many, many people who've worked on it all these years. And with that, those are Hubble's sort of classic discoveries, expectations in a nutshell. And I'm going to hand it over to Dr. Ken Sembach to tell us what we were surprised by.
Okay, so there probably aren't enough hours in the day to tell you what we've been surprised by with Hubble. So I'm going to give you just a little bit of a whirlwind tour of that. As Jennifer mentioned, Hubble was designed to do a lot of different things. And of course, many of the great things that it's done weren't even envisioned at the time that it was thought about or launched. A good example of that is exoplanets. There was one exoplanet known. First exoplanet was confirmed in 1992 after the Hubble launch. We'll come back to that in just a little bit. Some of the early motivators, like the Hubble constant, I think people understood and thought that it would be possible to determine the Hubble constant to 10%, which has been possible and which Friedman's team did. I think if you had told people back then that it might be possible to determine the Hubble constant to 1%, they might not have been so convinced. Well, today we know it to 3%. And we are right now working on making sure that we get it to 1%. Adam Rees and his collaborators are working on that. And that was not even possible until the last servicing mission because we didn't have the right instrumentation in place. In fact, at the last servicing mission, we didn't know that 1% precision was even within the realm of possibility. So same kinds of things could be said for just about all of the different topics listed up here, whether it's the ages of stars or black holes or dark energy or gamma ray bursts and so on. Hubble's touched all areas of astronomy and has made discoveries in all of these areas. I'm going to talk just a little bit today about a couple of these that you're probably relatively familiar with because they've been in the news a lot in the last few years. I'm not going to touch on things like Shoemaker Levy 9. Maybe you're going to mention Shoemaker, I hope. In that case, you know, there's a great example where you didn't know that it was going to happen. It was a once-in-a-millennium observation, and then, you know, another comet or asteroid hits the planet in 2009, you know, so it's maybe once a decade. If we're lucky enough and Hubble lives another decade, or maybe even to the end of this decade, maybe we'll see another impact on Jupiter. That would be pretty cool. Anyway, let's talk about dark energy for a few minutes. So dark energy is a relatively obscure form of energy that pervades the universe. And we know that it does in principle because we've been able to measure the expansion rate of the universe at different times. And the key to doing that has been looking at distant supernovae and looking at the brightness as a function of redshift or their distance. So what's happened over time, you can see in these plots here, the top galaxies show a galaxy with a supernova going off, and the bottom set of galaxies shows the same galaxy without the supernova. It may not be quite so apparent from where you sit, but if you do a visual comparison, you can see where the supernova is, especially in this last one on the right-hand side. Astronomers have used that kind of information to identify those supernovae with Hubble. They then know from looking at the spectrum of those supernovae what kind of supernovae they are. If they're type 1a supernovae, which have essentially a uniform mechanism for production and a uniform luminosity everywhere that they go off, you can deduce the distance. You know the distance because you can see how bright it is, you can measure how bright the supernova is, and you know what the intrinsic brightness should be. And so if you know that, then you know how far away it should be. You can compare that with how far away you think it should be from these different cosmological models that Jennifer alluded to. And what you find, at least for the more distant supernovae, is that they're dimmer than they would have appeared, or you would have expected that they would have appeared if the universe was just expanding and slowing down with time. And what the different groups looking at the supernovae at the time decided, this is Saul Perlmutter's group, Adam Rees, Brian Schmidt, the teams that won the Nobel Prize in 2011, they realized that in fact the universe was expanding at an accelerating rate, not a decelerating rate. And so instead of slowing down with time, it did slow down with time for a while, but then it started to speed up. That's, I've heard the analogy in a lot of cases that you throw a ball up in the air, and eventually, what you expect is that the ball slows down and then eventually comes back. Well, this is the equivalent of throwing a ball up in the air, and as it's slowing down, suddenly somewhere along that path it just decides to speed up and keep going up. That would be rather unusual. That would be a repulsive force rather than an attractive force. And that's kind of what you can think of with dark energy. It's a very repulsive force as opposed to an attractive force. So it works against gravity. So the folks in the Office of Public Outreach put this nice little video together where you can see the wow, it's got, I didn't realize it had sound with it. Turn that off. But what you can see there is that the galaxies start to come together, and then the rate that they're expanding away from each other is slowing down, and then suddenly they speed up. And so that's what's happening with dark energy. I won't bore you with the details of all of the different possible sources of dark energy. I am not an expert in that area, and so I really would bore you. But I just wanted you to know that that was one of the things. It's an obvious thing that we're going to be looking at in the coming years with Hubble. And there are several programs that are designed to investigate the nature of that dark energy, so stay tuned for that. Another obvious one that wasn't so obvious at the time, but now seems, why didn't we think about it? Why didn't we expect to find these things? Was debris disks, disks around other stars. In fact, the material out of which planets eventually form. And so back very early, right after Hubble was launched, even before the repair mission, there were pictures of the Orion Nebula taken, and inside the Orion Nebula, it was noticed that there were these darker little blobs, which eventually became known as protoplanetary disks, or proplyds. That's a word from the past, it seems. We don't use it too much, don't hear it too much anymore, because we look at disks of all kinds. But at the time, it was called proplyds. And these were little dark areas inside the nebula, and Bob Odell and John Bally and others realized that what in fact they were looking at was dust-embedded stars, and that these stars actually had these disk-like structures around them at the time. There were only a few stars known before Hubble's launch, a few, maybe 3 or 4, that had been observed from the ground to have disk-like material around them. This particular observation completely changed the paradigm of planet and disk formation. Here was an active star-forming region, turbulent, full of hot stars, lots of ultraviolet radiation, winds moving at millions of miles an hour, not too dissimilar from what you see in the Eagle Nebula, but a bigger region in that case, where you actually have very young stars, stars that might be only 1 million years old, with already evidence of disks around them. That was completely unexpected. And I think it will eventually be one of Hubble's legacy accomplishments. Here's a nice little movie that, again, the folks in the Office of Public Outreach put together. It's a kind of a fly-through of the Orion region. And you can see, as you go into this cocoon of material, I'm just going to stop it for a minute here so that we don't, so that we don't go through it too fast. Well, that didn't work at all. Let me try that again. I have to stop it inside the video. As you fly through, you'll notice there's lots of gas, but there's also stars, and then you'll see these little cocoons of gas. And these bright stars are early type stars. They're very young stars. They're putting out lots of ultraviolet radiation and light. And these little cocoons of gas are the forming clouds that will eventually become planets, planetary systems. And you'll notice that they have tails on them. So they're all pointed away from the very bright, intense stars that are illuminating them. They're basically being ablated from the outside. And you'll see as the video goes along here, and as we fly through, that there are lots of these little things, all kinds of little bow shocks and so on inside this region. And then it'll zoom in on one of these propylid type regions, and inside that, very interesting things are also happening, because this cocoon is being ablated from the outside, but it's also being consumed by the star from the inside. And as this material falls onto the star, it loses its angular momentum, and you actually form a disk, a flattened disk. And sometimes there's an accompanying jet out the bipolar directions. So this whole area of disks forming around other stars, very young stars, was very much new and very much Hubble. Hubble has observed disks around all kinds of stars now. Here's some recent examples from 2014 by Glenn Schneider and collaborators, where they see debris disks around some of these stars. These disks, unlike some of the ones that you just saw, are relatively devoid of gas. They're basically just dust. This is starting to get into the regime where you're getting into planet formation. That is, there's not a lot of gas left, there's a lot of dust still, and it's that dust that coagulates over time that forms planets. That brings us to our next topic. So you can think of discovery of disks and study of disks, and what does that naturally lead you to? It leads you to, well, once you form those disks, are there actually planets inside those disks? And here's a classic example from Hubble that's been looked at by Paul Callis and Mark Clampin and their group for several years now, in the debris disk around Fomalhaut, which is about 25 light years away. And you can see this debris ring, this dust ring around. The star is located at the center here, and there's a coronagraphic mask that's put in to block the light of the star. So this debris disk ring is very faint compared to the central object, so you need to suppress that light of the central star, and you're able to do that with Hubble. And you can see in the inset box here the location of a little blob of some kind in that debris ring in 2004, 2006, 2010, 2012, and its present location in 2012 when this particular image was taken. And it moves along a path, and they've deduced that, in fact, it's probably a planet moving in there. Now, there's some controversy about whether that's actually true or not, and why, and if it is, why this whole system should be as stable as it is. And again, we won't get into that here today, but it is probably an example of a planet that's been imaged by Hubble. Something, again, that we would not have expected. Now, I think one of the great accomplishments of Hubble is the fact that it opened up this whole field of studying exoplanet atmospheres. In 2002, Dave Charbonneau and collaborators showed that it's actually possible to measure the composition of a planetary atmosphere outside of our own solar system. They did this using a technique called transit spectroscopy. In this particular case, there was a star that had a planet circling it, and that planet and star were circling in a way where the planet passed in front of the star along our line of sight. And you can see in this little schematic movie here that the amount of light coming from the star dips just a little bit every time the planet passes in front of it. This particular technique is very powerful for determining the properties of exoplanets. And in fact, much of what we know about exoplanets is a result of this particular technique. In this particular case, if you want to study the atmosphere, you can do the same thing. You can measure the light from that star as it would be with just the star there, and compare it to the light when the planet is in front of the star. And this time, instead of just taking a picture of it and measuring the total amount of light, you can break the light into its component colors and take a spectrum. And in this particular case, they looked at the neutral sodium lines, and they saw that, in fact, the sodium line depths changed as the planet moved in front. So that's the sodium being absorbed by the atmosphere of the planet as it passed in front of the star. The same techniques now are being used to look for water, something that we didn't know was possible even 5 or 6 years ago. What's shown here is the absorption strength of that line as a function of wavelength. And that little black feature in the center of the plot there is, in fact, the new measurements from the Wide Field Camera 3 with a very particular type of observing mode that shows that feature very clearly. That's important because it's possible now to measure water on exoplanets of all different types with Hubble. We've been able to do that on hot Jupiter-sized planets. Recently, Frayne et al. Have measured water in an exo-Neptune atmosphere. Hubble can't do this yet for super-Earth atmospheres or Earth atmospheres. Maybe, just maybe, James Webb will be able to do that. We'll probably need an even larger telescope to do that in the future. But this is a nice result because it shows that, at least in some cases, exo-Neptunes have clear enough skies that the light from the background star can pass through and you can measure the water vapor content of the atmosphere. And again, around 1.4 microns where this water feature is, you can see this bump, and that fits models that have a nice clear sky rather than a cloudy sky. So there's lots of different types of discoveries. We can talk about those in the question and answer session. For the sake of time, I'm going to let Melissa carry on here. I'm sure you'll hear more about some of the discoveries from Melissa and Jennifer. So thank you.
Okay, the solar system from Hubble. Hubble's done an amazing job of observing the solar system. And it's been amazing both in the breadth and the depth of the results that it's achieved. There have been observations of every planet in the solar system except Mercury, and observations of every class of solar system object. And so I'm going to try to be very brief so we have time for the other speakers. So we're just going to dip our toe in to the vast ocean of observations and quickly bring it back out. And so I'm only going to talk very briefly about 3 things on this list, and I'll tell you at the end why I've picked the 3 that I did. So who here even remembers now that before spacecraft at Mars were almost as common as weather satellites at the Earth, Hubble did a fantastic job of observing Mars. The first guest observer program with Hubble was observations of Mars. Now, these aren't these aren't intended to be the best images. This is just a collage of observations from 1990 to 1993 that show you well how the view of Mars changes from the Earth as Mars' distance changes from its closest to its most distant. At its closest approach at opposition, Hubble did a fantastic job of observing clouds, polar caps, and in 2001, it even observed an amazing global dust storm. And so here's what the planet looked like right before the dust storm enveloped the whole planet, and the other 3 images show what the global dust storm looked like. But the real power of Hubble, as Jennifer said, has come because of its ever-changing and improving capability with time because of the addition of new instruments. And I love to remind myself how far we've come in 25 years. And so I've picked a couple of my favorite examples that show this really well. The first example is Pluto. This is the ground-based detection image made by James Christie of the Naval Observatory of the discovery of Pluto's first moon, Charon, in 1978. And then in subsequent images, I'm going to show you what happened over the next 22 years. Here were the first Hubble images with the faint object camera with spherical aberration in 1990. And although we had a really hard time convincing people that the telescope worked great even with spherical aberration, you can see for yourself that it actually did. And these were really amazing observations at the time. Post repair of the telescope, they were followed by these FOC images of Pluto and Charon in 1994. they have a less than an arc-second separation, and you can see how beautifully they're separated, and that you can now actually start to do observations of both the objects themselves, which were done. So starting then and for many years following, there have been spatially resolved observations of Pluto itself, the only such observations done. And from those observations, we've been able to make crude models of what Pluto itself looks like as its orientation changes. These are based on ACS images, and this was put out by Mark Bowie in 2010. But back to the satellites. So in 2005, not only can we now see Pluto and Charon really well, but there are 2 new satellites, P4 and P5. In 2011, we've added yet another new satellite, P4. And in 2012, we've added yet another new satellite. And so, as of today, here's the family portrait of Pluto. And I think you have to agree with me, we've made a lot of progress and come a long ways. And to me, these are really telling examples. They're also very powerful because they're simple, and anyone can understand the beauty and the power of these results. And of course, these are very pertinent still today, because next year, the first spacecraft ever will be flying by Pluto. And this year? Yes, it is 2015, isn't it? I think that you can agree that understanding the family portrait is pretty important. And so the next example that I'd like to give is Jupiter and the Jupiter aurora. Before Hubble, this was the best idea that we had about the spatial distribution of the auroral emission on Jupiter. And it was made with a spectrograph slit, scanning it back and forth and seeing where you saw emission and where you didn't. I remember really well in 1992 when John Caldwell had these observations with the faint object camera. These were the first images obtained of Jupiter in the ultraviolet, actually showing the aurora and showing the auroral oval. And at the time, we thought these were really fantastic. Very quickly, with a repaired Hubble and the faint object camera, we could start to see very fine detail. This is now the southern hemisphere pole and the northern hemisphere pole. With the WFIRST 2 in 1994, we could see both poles at the same time, and you can see the beautiful polar hoods that are caused by the hydrocarbons in Jupiter's atmosphere. But one of the most, I think, iconic images, at least for solar system observations ever made with Hubble, is this view of the northern polar aurora of Jupiter, in which now you can see footprint emissions from the satellites, so Io, Ganymede, and Europa. And then finally, with the advanced camera for surveys, these movies of images strung together where you can see the fantastic temporal variability of the aurora. And this really doesn't do justice. There have been just an incredible number of observations of Jupiter and Saturn of the aurora, and they're really stunning. We also now have observations of aurora on satellites. So Ganymede, Jupiter's largest moon, has beautiful aurora. And sadly, I don't have time to talk about much of this. I just want to say, in summary, I've tried to be very quick and leave further discussion to the questions. I just want to emphasize again that I've showed you how our ability and our knowledge evolved with time, and it's been, crucial that we had improving instruments with time to improve our knowledge. And the reason I picked these 2 examples and didn't pick Comet Shoemaker-Levy 9 impacts, which in my opinion was probably still the most fantastic event that Hubble's ever observed, was because these 2 things are very forward-looking as well as being backward-looking. And so I already mentioned this year, New Horizons will get to Pluto, and Hubble has been really instrumental in paving the way for that mission. And as you also know, fairly recently, Hubble was used to identify the next target for that mission. So not only has it given us a beautiful evolution through time, but it's still directly relevant to events happening this year. And next year, the Juno spacecraft will arrive at Jupiter. And these auroral observations are still directly relevant. So I've only given you a tiny little sample. There's just an incredible amount more to talk about, and hopefully somebody will ask me about something else during the question and answer period.
Okay. So now we're going to move from our solar neighborhood to the edges of the visible universe. Shortly after the correction of the optics of Hubble, Bob Williams, the then director, decided to do this really radical thing and point Hubble at a blank piece of sky for 10 days just to see what was there. And what he found was really incredible, that little patch of sky was basically filled with galaxies out to what we could see then without that camera with Hubble to 10 billion years in look-back time. So this effort was repeated as we got new cameras and new capabilities. Oops, sorry. There we go. With the Hubble Deep Field South a few years later. When we installed the advanced camera for surveys, that provided a much wider field of view, greater sensitivity in the optical, and the next director, Stephen Beckwith, observed the Hubble Ultra Deep Field. And then with the last servicing mission, we got the Wide Field Camera, which had Wide Field Camera 3, which had an infrared capability, and gave us an even more distant view of the ultra deep field. So the story of Hubble's deep fields is really the story of astronomers studying the history of the universe over 90% of its lifetime. And so what we've discovered with these deep fields is that galaxies existed less than 1 billion years after the Big Bang. We've been able to track the cosmic star formation history over 90% of the universe's lifetime, back to look-back times of 13 billion years ago. We're able to study those galaxies over that time in detail, and we can see that galaxies started off small and lumpy and weird and grew in size and mass and evolved in their shapes to the beautiful Hubble sequence that we see in the nearby universe of spirals and elliptical galaxies. Ken mentioned the results of supernova. So these deep fields are very popular. We go back to them again and again. And because we observe them so often, we can see changes. And many of the most distant supernova that have been so critical for helping to understand the expansion of the universe and the discovery of dark energy have been found in these deep fields. And then in concert with other great observatories like Chandra, we've been able to look at the host galaxies where supermassive black holes are. And we can see that galaxies can possess accreting very massive black holes as early as a few billion years after the start of the universe. So we've spent a tremendous amount of time with Hubble peering at this particular patch of sky, the Hubble Ultra Deep Field. And in 2012, the next director, Matt Mountain, asked the question, was there anything left for Hubble to do before the launch of the James Webb Space Telescope? Is there anything that it can do to learn more about the distant universe? And so he posed this question to a committee of astronomers. And of course, when you sort of dangle the prospect of lots of Hubble observations, the astronomers come back and say, yes, of course. So what they proposed was something somewhat different and radical. And that was to try to use what we call nature's telescopes, which are strong lensing clusters, to really peer deeper into the universe. So we have nature's telescope boosting the brightness of distant background galaxies observed yet again with Hubble, and that allows you to go intrinsically deeper, see intrinsically fainter objects than what we have observed with hundreds and hundreds of hours in the ultra-deep field without using all of Hubble's time. And then this committee also proposed to look at 6 clusters and 6 parallel fields, and that combination would probe a new parameter space, going to more fields, getting a wider view of the universe. And so 6 lens fields and 6 parallel blank fields equaled a really exciting new parameter space. So I'm going to show you this movie, also put together by our public outreach office, sort of demonstrates the power of gravitational lensing. So let me go back and play it again here. So Einstein's theory of general relativity says that massive objects bend space and time. Light traveling close to massive objects will have their light paths bent. So the most massive objects in the universe are massive clusters, and they act like nature's telescopes. So the background galaxies, as we would see in a blank field like the deep field, when they're behind a cluster, they appear brighter and stretched and magnified. And so this is what we're trying to do with the Hubble frontier fields. I have the privilege of being the principal investigator of this. We're observing these 6 clusters, and we're doing 2 per year over a course of 3 years. We're exactly halfway now. We have observed these first 2 clusters, Abell 2744 and Max 0416-2403. We're halfway through the observations of the second 2 the third and fourth cluster, and we've just received approval to go forward with the last 2 clusters. So this is an image that may be familiar to you. We did a big press release almost exactly a year ago at the last year's AAS of our first cluster, Abell 2744, and this has been in posters around the AAS. We've had a lot of exciting science coming out of this cluster. One of the things to keep in mind is that in this cluster, as a natural telescope, we have to understand the optics of that object. And it's overlaid in red here is a map of where the highest regions of magnification from this cluster are. And so along those areas of the darkest red are where we're peering into the universe and able to see galaxies magnified by factors of 10 or even 100. And that's where we're seeing these little sneak peeks of the deepest views of the universe. Have we succeeded? Yes, we're very pleased to have a discovery of an exceptional, one of the most secure candidates for a redshift 10 galaxy. So that's one of the most distant galaxies ever observed. It's also one of the most intrinsically faint objects ever observed. It's multiply imaged 3 times. It's basically 3 little red dots that appear right in those critical places where we expect the magnifications to be the highest. So this is our second cluster, Max 0416. Astronomers have been studying both of these clusters in great detail. And just with a third of the data in hand, these first 2 clusters and their parallel fields have really dramatically increased the number of intrinsically faint galaxies detected within those first billion years. And this is a real improvement in our understanding of what's happening with the formation of galaxies and the star formation in that early epoch of the universe. One of the other great things about this program is there's lots of other cool science that can be done with these images. So this is an image that shows the distribution, a model of the dark matter in this cluster. And so these lens galaxies, not only are they interesting in their own sense, but the properties, the lensing properties of those galaxies allow astronomers to map out the dark matter in those clusters. And because we have such exquisite depth and resolution, we're able to create dark matter maps of these clusters at unprecedented resolution and precision. And we're really thinking that this is going to help us understand the nature of dark matter and the distribution of the size scales of dark matter halos within these clusters. So there's lots coming. As I said, we're only halfway through our observations, and we've just received approval to do those last 2 clusters. I'm keeping my presentation pretty short here, but I would just say, the future is bright. What we're learning from the HST frontier fields are providing a sneak peek at what JWST will be observing. So on this plot, you can see, Hubble 2012, we're pushing a little bit past that with the frontier fields, but the epic of cosmic dark ages, I think, is something that, we're starting to push into a little bit with the frontier fields, but is something that will be easy for JWST. So I'll leave it with that and let Jason.
Okay, good afternoon, everybody. So my name is Jason. I'm the project scientist for the James Webb Space Telescope. I'm also a member of the science definition team for the WFIRST mission. These are two future telescopes that I consider the offsprings of the Hubble Space Telescope. And very happy here to tell you a little bit about those telescopes, but in the context of how they'll make the Hubble even more powerful in the future. And so in this final talk, I'll try and recap a few of the points that my colleagues have said, but with an eye to the future. So first, as you well know, Hubble's scientific reach is unprecedented. In almost every area of modern-day astrophysics, Hubble has transformed entire research fields. This is certainly true for my own field. I am fortunate enough to be the PI of 2 Hubble Space Telescope programs this year that are going to begin collecting data. And in both cases, I can confidently say that I'm trying to address science questions that have never been tackled about the universe before. And it's Hubble's tremendous sensitivity, resolution, and power that gives it these limitless bounds. As Jennifer said at the start, that said, Hubble was built with key science questions in mind. These are 4 of the pillars of the Hubble Space Telescope science case from the documents in the 1970s that Jennifer pointed to. This is what motivated much of the Hubble Space Telescope science case. But as Ken showed, the scientific discoveries from Hubble really blew away this vision that we had. And there are, these scientific discoveries really brought things that were in the realm of science fiction into reality, right? Jen is studying the bending of space-time as seen by Hubble through gravitational lenses. It's absolutely amazing. And so why is this so? Well, it's 2 reasons. I mean, one is Hubble has this amazing discovery potential that Jennifer alluded to. But it also, Hubble has changed the astronomical landscape. By making its scientific discoveries, Hubble has transformed entire research fields. And the most important, best tool that we've had to then characterize objects in this new astronomical landscape has been Hubble. And so through the servicing missions, Hubble has been able to follow up some of its own discoveries and learn more about the universe. Ultimately, it's not just the discovery of an object that matters for scientific progress, it's understanding what that discovery is telling you about the universe. And Hubble has excelled in that countless times. And one of the reasons that Hubble is so powerful for this is its versatility. Right? Today, Hubble has multiple cameras that can see ultraviolet light, both with imaging and spectroscopy. It has multiple cameras that can image at visible wavelengths. And it has multiple modes of science operations, including imaging and spectroscopy at infrared wavelengths. But 80% of the science case that comes from Hubble, 80% of the scientific discoveries are happening at a wavelength that's shortward of the infrared bands. And that's going to be very important as we go forward. So over the last 15 years, astronomers have been asking what is the next astrophysical frontier as we look beyond Hubble? And astronomers have done something that's very logical. They've motivated 2 scientific missions that expand Hubble's discovery potential by 2 orders of magnitude. So one is the James Webb Space Telescope. This is a telescope that roughly will be 100 times more powerful than Hubble. And the other is the WFIRST mission. And the WFIRST mission operates at the same power as Hubble, at the same resolution as Hubble, but it can see an area of the sky that's 100% bigger than what Hubble sees. So there are many different scientific examples that I can use to motivate this and show this. Let me just use one that Jen also alluded to, and that's our ultra-deep field studies. And so this is placing the ultra-deep field into some context. in the sense that when we look at this deep field, we're looking at a tiny, tiny part of the universe. And Hubble showed us that in this tiny part of the universe, we can count 10,000 galaxies. And so if you ask yourself, well, how many of those tiny parts of the universe does it take to fill the entire night sky? Hubble actually tells us what our place in the universe is. And so through the eyes of Hubble, our place in the universe is that, we're sitting on a rock, orbiting a star, and that star is one star out of 100 billion in our galaxy, but that galaxy is one galaxy out of 100 billion in the universe. Absolutely amazing discovery. But Hubble doesn't just count galaxies. Hubble has actually gone in and placed these galaxies into a cosmological context. It's told us what these galaxies are telling us about the early universe. And one of the things that we've learned from doing this with Hubble is that if we look at the most precious objects in this image, the furthest objects whose light has been traveling to us for the longest amount of time, those galaxies already appear to be mature systems. They're not the first galaxies that transition the universe from a dark, boring place to the brilliant, luminous universe that we see nearby today. And so one of the next frontiers is to find those galaxies using a telescope that's more powerful, like the James Webb Space Telescope. At the same time, as Hubble has opened these windows, and again, I'll use an example of the ultra-deep field here, Hubble has opened these windows all over the universe, many, many different windows. We have to recognize that these windows are extremely small. Every one of those Hubble Space Telescope windows is about 50 times smaller than the size of the full moon on the night sky. And so often when we look for the most interesting objects in these windows, we find that those objects are few and far between. We can see a couple examples of redshift 9, redshift 10 galaxies in an image like the Hubble Ultra Deep Field. And so with this WFIRST mission, what we'll essentially get is every time we take an image, it'll be an image that'll have 100 times the statistics as we see with the Hubble Space Telescope. And so where we see 10,000 galaxies in the Hubble Ultra Deep Field, in a typical WFIRST Deep Field, we'll have 1 million galaxies. Where we see a couple galaxies that might be redshift 10 galaxies, we'll have a couple hundred galaxies. And so again, our statistical sense of what's happening in the universe and our interpretation of what those sources mean for the universe will expand exponentially with these tools. And so the scientific motivation behind JWST and WFIRST is vast, and this is my attempt at taking a 1-hour presentation and squeezing it into one slide, since Ray Villard has given me 5 minutes for this. But to me, this scientific vision, as bold and impressive as it is, really is kind of like those 4 pillars in the Hubble Space Telescope vision from the 1970s. This is what we think today these telescopes are going to tell us about the universe. What we actually find with these telescopes will likely blow this out of the water. But then, as that astronomical landscape changes once again in the 2020s, how do we actually progress science? Well, to progress science, we have to characterize those discoveries. And these 2 telescopes, the James Webb Space Telescope and WFIRST, are both tuned to see infrared light. And what we've learned from the Hubble Space Telescope is to truly characterize the universe, we need to have a panchromatic eyesight. We need to be able to study the most interesting objects at multiple wavelengths to figure out and interpret that light. And so in this era, in this changing astronomical landscape, Hubble will be the only, Hubble will be the only game in town that can see panchromatic light, provide UV imaging, UV spectroscopy, optical imaging, optical spectroscopy, along with the discoveries that we'll make. So I have no doubt that in the 2020s, in the era of JWST and WFIRST, Hubble will become even more powerful than it's ever become before. Thank you.
Thank you very much. Well, we've technically run out of time, but I think we'll take a few extra minutes and see if we have any questions, because it's a lot to cover. So Zolt LeVay from STSCI will be our mic handler.
Hi, Jeff Faust, Space Review. Question for Jason. Talking about this last slide here, have you started to think about things like how to best leverage the synergies of James Webb and Hubble when they're both up there and flying at the end of this decade? in terms of joint observations or other capabilities?
Yeah, absolutely. So at the Space Telescope Science Institute right now, we're planning to operate these two telescopes jointly, and the mission offices, the Hubble Space Telescope Mission Office and the James Webb Space Telescope Mission Office, are discussing ways that we can allow people that have excellent science ideas that require both facilities to take data of the same targets to be able to get those data sets on both missions. So, we're in the process of putting together policies that are going to ensure that that's possible. At the same time, the program analysis groups that NASA has are looking at what exactly those scientific synergies will be, and so we can motivate such studies in the future.
Any other questions? Okay, we got a couple more down front. We'll take Ron Cowan first, and then we'll go back over here to Glenn.
Ron Cowan, freelance. For Melissa, can you say a little bit about why you think Shoemaker-Levy was such a phenomenal event in the solar system for Hubble to see, and maybe talk briefly about one or two other things that you didn't get a chance to cover?
Well, I tried really hard to stick in a couple slides, and it was just impossible to try to capture it. And so I thought, maybe if somebody asked me, I'll try. It was back when we were still, I started working at Space Telescope Science Institute in 1992, and for quite a few years around, spherical aberration, I had great science data, and I would go out and talk about it at meetings, and people would say, oh, we don't believe you because we know the telescope's not working. Every article about NASA would talk about the failed Hubble Space Telescope. So I don't know if you remember the AAS meeting in January of 1994 when John Trauger got up and showed a result from WFIRST 2. I think he showed a color magnitude diagram of a cluster, and it was just absolutely stunning. And that was when we knew, that the telescope had been fixed, and it was just an incredible moment that he got a standing ovation. Everybody was into. So we were still sort of in that era of it was the failed Hubble Space Telescope, and this was a tremendous event that got unbelievable media attention. So the reason why I still think it's the most incredible event was that there were TV trucks parked out in front of the Institute. We had guards at the Institute to get in. Bob Williams got stopped and they wouldn't let him in. He was the director. And also the 6 PIs of the Hubble programs we were all relatively young. The sort of older, more experienced people had sort of taken a pass on this event. And we sort of stepped forward and said, heck, why not? If it's a failure, what have we got to lose? There were a lot of predictions that it was going to be a complete fizzle. And, I bought 2 bottles of champagne. One we had the night before just in case it was a flub. And the other one was the bottle that got passed around at the press conference that Gene Shoemaker drank out of that I still have. And so it was, there was a lot of tension because we had no idea. And then the day of the impacts, we had an exploder, and we got the email that said the first impact was observed at Kalirai with a brightness in the infrared brighter than Io, which is very bright. And so we were all like, oh my God, we couldn't believe it. And then we all got really nervous and said, oh, what if Hubble doesn't see anything? We were like, oh my God, that would just be a disaster, right? So we were just really nervous, really excited, and I just can't describe to you what it was like to see the first images where we saw the plume and then the subsequent. It went on for a week. Hubble had just storybook data. And, we all were sort of thrust into the limelight. We all did press conferences, radio interviews. I went all over the world talking about results for 2 years after that, and got to do things like meet James Van Allen, who's and so it was just an unbelievable event, and it was definitely in the top 5 in my career, and it was so much fun. It was nerve-wracking, and we also worked really, really hard, and we had fantastic storybook data. So, and I think also Gene and Carolyn Shoemaker, right? It was sort of like mom and dad leading, were like the iconic scientists, and David Levy, who had made this great discovery. And it was just you couldn't imagine a nicer person than Gene or Carolyn. And so they were sort of, thrust forward, and you couldn't think of two more deserving people. And so it was an incredible event. I can't really tell you.
Another thing that a lot of people don't remember because it's just been so long is that was the first scientific event that played out on the internet. The World Wide Web had just begun to become common, and all of a sudden people had a real motivation to get onto it. And a lot of the publicity came because people from all over the world were able to watch essentially live.
I just have to add one more thing, and that is that, there were films and videos of that, us seeing the first images, and still to this day, 25 years later, people come up to me and say, "Oh, I saw you on the Discovery Channel just yesterday. I heard your voice, and I knew that was you, right?" So people I work with now who didn't even know me then, they say, "Oh my gosh, we saw you on the Discovery Channel." So it's still being shown. And so I think it's amazing.
Down here.
Hi, I'm Greg Scheiderer with Seattle Astronomy. My question is about the future of Hubble. I mean, it's 25, and we've been told there will be no more servicing missions. What's your most realistic hope for how much longer it will be functional? And if there could be a way to service it again, would it be worth it?
I can start and you can
Go ahead.
complete. Well, as I mentioned, right now the telescope is in fantastic shape. We have this wonderful suite of science instruments, multiple cameras and spectrographs. The last servicing mission, we were able to put in more gyroscopes, batteries, and so forth. So it's in great shape. It's very hard to predict when things might start to fail, but you do the best you can. And so right now we're pretty confident, and Ken, you can add to this what your perspective is, but we're pretty confident that the telescope will work well into the 2020s at least. And so our little motto right now is Hubble 2020, because we really believe that Hubble can be fully scientifically productive at least until 2020, and we want it to overlap with the James Webb Space Telescope. That would give us some particular scientific advantages. But we see no reason why Hubble couldn't continue operating many years beyond that. So that's our perspective at the moment. There's another piece of information here, however, that's very important for science, which is that all these years, and in particularly the current years, is we've been very conscientious about making sure that the data that we gather with Hubble is put in an archive that's easily accessible by future astronomers. So even now, about half of the published papers that are coming out based on Hubble data, new information in scientific literature, is based on archival data that was observed perhaps for a different purpose some years back, and then an astronomer will delve into that archive and derive new information out of it. And so we're conscientiously making sure that very good data sets are being put into that archive so that for many, many years beyond even when Hubble's operating, we'll still be making Hubble discoveries. So that's part of my perspective. Do you have something to add?
Yeah, I'll just add a few quick things. It's important to note that, the last servicing mission occurred 5.5 years ago. Consider the following. The repaired instruments, the Space Telescope Imaging Spectrograph and the Advanced Camera for Surveys, have now operated longer on their repaired electronics than they did on the original electronics. That's very encouraging because it suggests that any infant mortality in those electronics is gone, right? It doesn't mean they're going to last forever, but it means that those kinds of things that doomed those instruments early on probably won't be the same types of things that get them later. The two new instruments that were put in, the Cosmic Origins Spectrograph and the Wide Field Camera 3, are still operating on their first electronic side, and so they have redundant electronics. Gyros, which have been a life-limiting factor for the observatory, or a capability-limiting factor for the observatory in the past, are not now a life-limiting factor for the observatory. We have 5 of 6 gyros working. We lost one last March, which was expected. We know how to operate Hubble now with only a single gyro operating. And so we will operate on 3 gyros as long as possible. But once we get down below 3, we'll turn one off. We'll operate on 1 gyro. we should easily be able to get into the early 2020s with the complement of gyros that we have now. NASA did in 2013 a very extensive engineering study of the various subsystems and the instrumentation on the observatory. They called in experts from the different field centers to take a look at that information, and they've indicated to us that they think that there's a very healthy probability of getting out to at least 2020. That's great, as Jennifer was mentioning. Within the project, at Goddard and at the Space Telescope Science Institute, we're conducting what we're calling the 2020 vision for Hubble, and that is to make sure that the observatory is ready to run for another 5 or 6 years, to get at least a year of overlap with James Webb, if not more. And we're lucky in that we have very proactive engineering that's been going on over the last few years and continues to go on both at the Institute and at Goddard to make sure that we're operating the observatory as safely and as effectively as we can. So we're going to get to 2020.
Go ahead, Melissa.
So I just wanted to add one more brief comment, and that is that there is no plan to replace the UV capability of Hubble right now either, right? I mean, it's being talked about, and those kind of telescopes have been talked about for 20 years now. And when we lose that capability, that's a huge loss. And so some of the major discoveries in my area made in the last couple of years, plumes on Europa, for example, have come from UV observations. And so I'm rooting for way longer than 2020 myself until we get a UV replacement plan. So.
Larry, are there any questions on the web?
There are no questions from the web.
Okay, good. Then we'll wrap it up. I want to thank our speakers again, and I want to just point out that it's delightful 25 years after the dismal summer of 1990 to use the phrase 2020 in connection with Hubble instead of 2200, you know? So our next press conference is tomorrow morning at 10:15 a.m. on black holes and binary stars. I want to remind you that tonight is the infamous astronomical party, the after party, the Wednesday night party, which tonight will be held beginning at 10 p.m. at a pub called Neighbors off Pike Street. There's a little card being passed around the conference, and also it's posted on the bulletin board in the press office. And finally, if you attended the press dinner last night and you haven't paid me yet, don't forget I have your contact info and I know how to find you. All right, thank you very much. We'll see you tomorrow morning at 10:15. You're very welcome. Thank you for doing that.